listed the 3 kinds of uncertainty. But now to put them into a little bit more specific context, we're going to basically talk about 2 different models today. Okay? The dynamic one is going to look completely different from anything we've talked about up until now. Some of the graphs will look the same, but the essence of the model is very different. The scientific and strategic uncertainty parts are going to look a lot like things you've seen already. Okay? When I talk about scientific uncertainty, I'm really talking about uncertainty in the social marginal cost curve. Okay? We have no idea what drinking Gen X does. Maybe it gives you all sorts of bad diseases, cancer, genetic problems, etc., or maybe it's harmless. Probably not, but we don't really know how big that is. Strategic uncertainty is uncertainty all about how valuable emissions are to firms. So we can either talk about that as being uncertainty in the marginal benefit from emissions or the marginal cost of abatement. Same thing, right? But if emissions are really, really valuable to a firm, and we put a tax in place instead of a standard, we're giving the firm the freedom to produce a lot more emissions and just pay more tax. And under certain circumstances, that's going to be a really bad idea. Okay? That's the gist of where this is going. The dynamic uncertainty part is really all uncertainty about, we know that there's a social marginal cost in the future with some probability, but with some probability it won't be there at all. It's sort of a either all or nothing sort of a premise. Okay? So it really fits in with climate change well. Because even if you're going to argue that you think that there's only a 20% chance that climate change is actually a real thing, or a 10% chance, we're going to argue that there's still a rationale for doing costly abatement today. And the question is, how much abatement today would you do? Okay? The idea of waiting to see in the future requires a lot of additional argument to make that make the argument that we should wait and see. That's the point of that story. Okay. So I said the first 2 models are basically going to look like what we've seen before. So we're going to start off with that same kind of graph. So before we talk about any kind of uncertainty, let's just pretend we're in a world where we know everything and then work from that. Okay? So we've got our social marginal cost curve and our private marginal benefits, and we're going to be comparing 2 policies, a tax that I'm always just going to label as T, okay, and a standard that's going to be E hat. So I didn't label it as E star because in a minute that might not actually be the optimal thing, but let's just say that you can either put into place an upper bound on the amount of emissions that you can produce, or you can put into place a tax where you're going to pay for every unit that you produce, okay? And in a world where we kind of know everything, we don't really, both of those policies are identical, right? Under one, the firm actually has to pay for all the units of emissions it produces. Under the tax, under the standard, they just have to pay to clean up, but that's just money either going into taxpayers' pockets or the firm's pocket, which from our point of view, we don't really care. Okay, so no difference there. But now what we're going to do is ask, is there any difference in those 2 policies if the pollution is like Gen X and we don't know how big the social marginal cost curve is? Okay. One thing I kind of want to make a point here is that it's not just the social marginal cost curve that we don't really know. If you think about what that SMC curve is, right? It's the private marginal cost plus the marginal external cost. If you go back earlier in the graphs, earlier in the slides. Marginal external cost, the marginal part, means that that's the additional number of cancer cases from 1 more gallon of Gen X going into the Cape Fear River. Okay? It's not the total number of cancer cases for a certain quantity of Gen X. It's worse than that, trying to figure it out. It's the slope of the function that describes how much more cancer you get with every additional gallon. Okay? So we might have a pretty good idea that a lot of Gen X will cause a lot of cancer. We don't really have that clear yet, but you might think that that might be the case. But we need more than that to get the social marginal cost curve. We need the derivative of that function, which is really hard to get when you barely even know what the function itself looks like. Okay? So the practical things we don't generally know, aside from the math of getting the derivative of a function like that, is we don't know who to lump in, who all is affected. So in the Gen X case, is it just the people who live right along the river? Does this water work its way out into the fish supply, and then away from the river. We don't actually know the health risks. You need a lot of clinical studies and epidemiological studies to know this sort of thing. Once we know how many people are going to die from those cancer cases, then we have to actually figure out how much to value those things at. Remember, everything on that graph is in dollar terms. So you can find economic studies that say that number should be $500,000 per death, and you can find studies that say it should be $12 to $16 million per death. Right? And that's going to make a big difference in terms of the slope of that line. We'll talk about how you do this specifically in November, and one of the groups will get assigned a project, or you'll pick the projects, but one of the things you can pick from will be doing this sort of an exercise. So you'll come up with a number, and you'll see how hard it is to get that number. Okay? And then even aside from all the cancer cases and who's getting it and how much their life is worth, we might actually worry about other stuff besides people. So the ecosystem in general could have value, right, that we worry about for other reasons. And that's an even harder thing to measure because, well, we have an easier time measuring the value of things that we call anthropocentric, stuff where people make decisions, because when people are the ones expressing their value, they go out and buy things. And they spend, resources on stuff that helps us figure out what it's worth to them. We don't see fish go out and buy things. We don't know their willingness to trade off clean water for other goods and services. Okay, so that's tough. And without knowing it, we don't really know, for instance, whether that social marginal cost curve cuts right through here, or is it higher than we thought, or is it lower than we thought? Okay? And this just isn't saying that there's more deaths. This is saying that the slope of the curve relating Gen X to deaths is steeper. Right? That's what it means for this line to be up here, and this says it's flatter. Right? So what's the implication if we don't know where that line really is? And we really don't for almost any pollution that's out there. Even for pollutants we know a lot about, there's still a lot of uncertainty as to where that line is going to lie. So the key thing about scientific uncertainty is that it doesn't really matter from a policy point of view. Okay? So if you ever hear anybody make an argument that one of these two policies is better than the other one, based on the fact that we don't know enough about the pollution and what it does, that's a bad argument. You can argue against that with the picture that we're about to show. Okay? There's no difference in policy choice. Right? You want to have a policy in place because just letting them do all the pollution they want is clearly not good. Right? You way down here have lots of dead weight loss you could recover. But the point here is that if you have the tax in place or if you have the standard in place, the firm is always going to be producing at this point. Okay? And the reason is because the firm, in this case, the Teflon making company that produces the Gen X, doesn't care at all about where these social marginal cost curves are. Completely irrelevant to the firm, right? They care about the tax that they're confronted with or the standard that they're confronted with and where that lies relative to their marginal benefit curve from making the Gen X. Those are the two curves they care about, the tax and the marginal benefit, right? And the standard, if that's the policy that's in place, right? So the firm's not going to change its behavior at all if the social marginal cost curve is high or if it's low. They're going to keep doing the same thing. We're just going to end up with a different deadweight loss. Okay? But the deadweight loss is going to be there regardless of which policy we picked. So if we turn out to have the high social marginal cost, so I've labeled it with an H for high versus low, we're going to wish we were here. Okay, so on the slides, if you're looking at them close up, there's a little dashed circle there, and that's the optimum point. I try to use the dashed circle for that. Right? That's where we would like to be if we have a high social marginal cost. Where we're going to end up is down here at the black circle, and what we do if we get the deadweight loss, if we're trying to calculate the deadweight loss from this mistake, is take the difference between those 2 points in emissions and see how much the social marginal cost exceeds the private marginal benefit for every unit. And it adds up to the red triangle. Okay? If we had the low social marginal cost, then the policy that we have in place is too strict. We would have liked to have been down here. I didn't label it. as anything, but you could label that as E8 or EL, okay? And now the deadweight loss is we'd like to be here, right? More pollution. We're going to be back here, too little pollution. So we take the amount by which the benefit from every unit we didn't produce exceeds the social marginal cost. And we get that yellow triangle, all right? This is the kind of graph where people start to make the mistakes of like coloring in that triangle or that triangle when I ask them for deadweight loss because it looks about the same. It's kind of in the same place, right? But two things to think about. Where would you like to be? Where are you going to be? And by how much does the benefit from every unit of emissions exceed the cost to society? Or does the cost to society exceed the benefit for every unit in between those? Okay? And if you just go through it with that kind of logic, you'll always get the right triangle to color in. Okay? And this is the kind of thing like this, or in a second we're going to do it when the uncertainty isn't about this line, but it's about this one, and then things get messier. And the problem set questions that will come out at the end of next week when we write the next problem set on the exam asks you to identify these triangles, and on the problem sets I ask you to measure them and things when you have more time. That's the sort of thing that you have to do, okay? So, all right. So are we good with scientific uncertainty? Yeah.
What does instrument choice mean?
So instrument choice basically just means tax or standard, okay? This stuff all comes out of a famous paper, just to give you the names of the people who are involved with this kind of stuff. A Harvard professor named Marty Weitzman does environmental economics and a variety of other things. He's pretty close to retirement now, although he just gave a talk this summer at the meetings we had up there. He wrote a paper in the 1970s called Prices versus Quantities, which kind of made this point for the first time, where he was talking about, is it better under circumstances like this to use prices, which is basically removing taxes, where you put a price on the pollution, versus a quantity restriction, which is the standard, okay? And when we talk about tradable permits next week, when we have the trading game, and then on Wednesday we'll go through the actual theory of permits. Permits are really the same thing as standards. It's just once we make the standard, we allow firms to kind of give some of their standard to a different firm, and they can trade them back and forth if they want. They can cut the standard up and trade it around. But a carbon tax versus a cap and trade system is kind of what you would expect to see in the newspaper if you were arguing about this sort of thing, okay? And in general, economists really like carbon taxes because there's a lot of stuff that gums up the system with cap and trade. There's a lot of like institutional stuff you have to put into place. Whereas with carbon tax, you just say, you know, everything you burn has a certain amount of carbon in it. You pay us based on how much is in that. We're going to see in a few minutes why carbon taxes might not really be good for something like, for the sort of uncertainty reasons that we're about to talk about. Carbon taxes might be noticeably worse than tradable permits. Okay, so here's how that sort of story plays out, why we see one of these things now be worse than the other one, okay? If the uncertainty is actually about the marginal cost of abatement or the benefits to the firms from making more pollution, so I call this strategic uncertainty because if you were to go ask the Teflon company making the Gen X, how much is it worth to you to make more Gen X? They would probably say, it's really not worth very much to us, right? So that you would think that their value of it is really low, and then they would therefore give you a really, like, you know, I'm sorry, I had to say that around. They would say it's really worth a lot, so they would be willing to give you a very high emission standard on it, right? If this is super valuable to the firm, then it's going to be costly for them to clean up, and from a social point of view, you're either going to want to give them a low tax or big standards that they can make a lot, okay? But in reality, that might be quite different. It might not be worth nearly as much as they're going to tell you, so I'm going to call this strategic uncertainty because the firm can lie if asked, right? They're probably going to overstate the value of this so as to try to be able to get a lower tax even on the stuff that they're going to produce. So with that in mind, let's just say that, you know, we could end up with different marginal benefit curves from the ones that we start off assuming. So here, the solid line is the one that we started off with. You know, now we know the social marginal cost curve with certainty. If we think it's this line, we would have set the tax there, we would have set the standard here, okay? But then we realize next year when they start producing that the marginal benefit was a lot higher than they told us, right? It's actually like up here, MB high. And as a result, if the standard was in place, what amount of janks would they be producing? Well, they wouldn't have a choice. They'd like to be producing a lot more, but we would have stuck them down here at E hat. The standard doesn't change just because the value of the pollution is different. And if the tax were in place, now we would have this downward sloping line, and the firm doesn't care about the social marginal cost curve, but it cares about the tax and its own value, so it's now going to produce more and more pollution up to the point where those two things are equal, okay? So the key difference between strategic uncertainty and scientific uncertainty is that under strategic uncertainty, when things change, the firm actually changes its amount of pollution under the tax in this case, whereas under the standard it stays put. All right? So that's why there's a fundamental difference between the two. And it's because the firm cares about its marginal benefit curve in making decisions, but it doesn't care about the social marginal cost curve. Okay? So now we're going to end up with deadweight losses, but the deadweight losses could be very different depending upon which policy we pick. Okay, so I've tried, I think, to maintain using red things to indicate the standard and blue things to indicate the tax throughout all the coloring in graphs here. Okay? And what we're going to end up with are these butterfly shapes, all right? Where with the new marginal benefit curve, we would have liked to have been right here, where the social marginal cost curve equals the private marginal benefit, okay? Well, with the standard, we're going to end up back here, where the firm was initially stuck and they can't make any more. With the tax, the firm is going to compare their private marginal benefit, the new higher one, to the tax and produce out to this point, okay? So we've got that difference. But now the deadweight losses, we take where the firm is going to be under each of those policies, compare it to where we'd like them to be, and take the difference between the benefits and the social costs. So here the benefits are bigger than the social costs, which means the firm isn't making enough pollution. Here the benefits are a lot smaller than the social costs, the firm's making too much pollution. Okay? From an economics point of view, both of these are just equally bad deadweight losses. So you have to kind of check your environmentalist credentials at the door and say, it's just as bad, right, for there to be too little pollution as for there to be too much pollution. Both of those things are, you know, deadweight losses. Yeah?
So the difference in where deadweight loss is drawn between the scientific uncertainty and the strategic uncertainty is that the scientific depends on what the actual social marginal cost is, and the strategic depends on whether you had a standard or a tax.
Yeah, so I mean, it does, both of these depend upon the actual social marginal cost. But the only thing that's moving in this scientific uncertainty is the social marginal cost. So the key thing here is that the firm stays at this point no matter what. Under the tax and the standard, the firm doesn't move. Where we'd like them to be moves. So we end up getting deadweight loss triangles, but basically, if the social marginal cost was higher, we would have gotten deadweight loss triangle A under both the tax or the standard. It wouldn't have been any different. Or we would have gotten B if it had been lower. But now we're going to get, under strategic uncertainty, we're going to get the blue deadweight loss triangle if we put the tax in place, and we're going to get the red one if we put the standard in place. Okay? So I've rigged the first graph, so that's a perfectly symmetrical butterfly. And we would say, okay, it still doesn't matter, right? And if you're kind of good with just, you know, geometry and drawing straight lines, you can kind of see that that's going to be true if basically the social marginal cost and the private marginal benefit have the same slope. Just one's the opposite of the other, right? So now what we're going to do is start to vary that and ask how it's going to change things. Yeah?
Can you explain again why we have that higher marginal benefit curve?
Yes, that's just the firm kind of ex post after we set the rule at E hat or at T. So we've either set the tax or the standard, and it's now written into law. But then we realized afterwards that the firm's benefit from making pollution was a lot higher than we thought.
So the company claimed to be the lower marginal benefit, but its actual benefit is higher.
We could say we went out, when we set the rule, we went out and asked them what their benefit was going to be, and they said it's a low number, right? So, and then we find out later that it actually turns out to be a higher number, or it's a higher value. I think I was getting the argument about the strategic thing mixed up pretty badly about 10 minutes ago. So hopefully you guys all follow what I was trying to say, right? Here the firm would probably, in order to get a more beneficial standard, it probably would have set a higher number, right? And then it would have actually come in with something lower in reality, right? So they could have gotten more generous standard put into place. This is probably the opposite of what would really happen if you had a strategic thing where the firm was lying. But it could just be that the firm didn't know, and then they find out 6 months later that their benefits from making emissions are actually really different from what they thought. It doesn't have to be nefarious. Okay, so here's what happens when we start to get the sort of deformed wing butterfly, right? When things start to get different as a result of the slopes starting to vary, okay? So now, let me blow it up. It's hard to kind of see the detail in there. But now we've got our new private marginal benefit curve that's higher and our social marginal cost curve going through there. So there's our point where we'd like to be, where those two triangles are just touching. And where we're going to end up being under the tax is where the benefit curve crosses the tax line, so out here. And under the standard, we're still going to be stuck back here. So now the deal is, what does it mean for the social marginal cost curve to be really steep? If you put that into words, what would that imply? Yeah.
Every next unit of output has a high cost on society.
Yeah, every additional one has a really big cost itself. So say we have a social marginal cost curve that's going along and it's really even just flat, and then it gets really steep all of a sudden. Give me an example of like something that could be something that we heard about at the beginning of class today.
I mean, maybe like the Gen X, if you only have like up to this much Gen X in the water, like it's an okay, it's not a huge problem, but then
And a little bit more.
Once you pass like a certain threshold,
Yeah. I mean, so Gen X, we know really very little about it, so I would argue that it could turn out to be that way, but we have no idea at this point. It could be very much every unit has another cancer case, and that's basically it. Right, but the ice sheets falling off, for instance, falling off Antarctica or melting off of Greenland, these are the kinds of things where some scientists would argue if we just get above a tiny little bit too much carbon in the atmosphere, we're going to hit that point where the circulation makes it drop off, and then we get, I'll have this up in a minute, but 10 feet, I think, like overnight, of sea level rise if the West Antarctic ice sheet falls off, and I think we're talking 7 meters, so like 20 feet-ish, if the Greenland ice sheet melts. So you could end up very quickly, right? 20 feet is pretty severe in terms of, it's like water world kind of like stuff going underwater, not big storm type. So that would be a really steep component in the social marginal cost curve. Okay. So you can kind of see, if you think about the intuition for it, what we don't want to do in a world where 1 more ton of carbon could make an ice sheet fall off is give the firm the leeway to make more carbon if they realize their marginal cost of abatement was higher than they thought. Right? We'd like to stick them back here at a point where they can't go any further, and then if they realize that their benefits for making carbon are higher than they thought, well then they're just going to incur this little deadweight loss triangle for not making enough carbon. Right? But we avoid the risk of ice sheets falling off, which give us really big deadweight losses because the social marginal costs are super high. Okay? So that's why we played the tipping point story at the beginning. That was kind of the story there. And these are some, just to go back through the tipping points that they brought up in that podcast, and it's part of a bigger podcast that's on the Sakai site if you wanted to listen to the rest of it. But sea ice is a big one, and people talk about both tipping points and sort of feedback effects with climate change a lot. So, does anybody remember in the last 4 or 5 years what the big sort of argument was about the sea ice problem and like how that affected the weather in the northern part of North America in general, I guess in Europe too? There was a big sea ice argument about whether this was the result of, do you guys remember the subpolar freeze kind of thing where in North Carolina it dipped down below like 0 for a few days, got down to like -10. Was that before you all got here? Okay. But this happened probably in places you were from. If anybody here is like from the Northeast or from the Midwest. You guys remember there was like a point in time when you couldn't go outside during the school days. Face touched the air for more than 30 seconds, you could get gangrene. No? You guys don't remember this? It wasn't that long ago. Maybe you all like elementary school. I don't know. They thought that that was because of a breakdown basically in the jet stream, which was the result of the Arctic ice sheet not having built up for over the course of the winter enough. And basically what happens is when this gets really cold, it kind of creates an effect that extends down and keeps the jet stream going and keeps the polar air from like working its way down into North Carolina. But when the jet stream breaks down because this sort of circulation on the North Pole breaks down, we end up getting sort of polar weather here. So you get super cold weather, and then all the people go on certain news programs and say, okay, so there's no global warming because we're going to freeze to death. But they don't get the idea that it's all tied up in that. Okay, so that's like your little bit of atmospheric science there. This one I found to be kind of interesting, just because it's really not how big the Greenland ice sheet was. But there it is if you were to lay it out over Europe. So it's pretty big. And this was now kind of dated, but just over 10 years, how much it started to shrink. And essentially they say that there's the equivalent of about 7 meters of sea level frozen in ice on Greenland. So if it all melts and flows off, we get the really, really big sea level rise. And I know since 2002, there's stories that you can find on NPR if you go and listen, where big cracks have developed in this, and big chunks are starting to break off and flow out in rivers on the ice sheet. So there's a lot you can look up if you're interested in those kinds of tipping points. Here's a simulation of what Boston would look like under a 12-foot sea level rise, which is the kind of thing you'd get if you had the West Antarctic ice sheet fall off. So it's currently suspended, it's not floating, and if you drop ice into a glass, the water level rises, right? And if it's not floating in there, the water level's not gone up yet. So if the ice sheet falls off, and actually some pieces of the ice sheet have started to fall off in the last few years. And they talked a lot about these other non-sea level rise related things, breakdowns of sort of big ecosystems around the world, which would have huge effects on people's ability to grow things. So this would be, we're not talking about sea level rise, we're talking about famine and that sort of thing. So there's a lot of reason to be concerned about, I think, the big tipping point problem and the steep social marginal cost curve. And now what I'm going to do is show you the alternate side of the story, where the social marginal cost curve is pretty flat. This would be the case if every gallon of Gen X did just create 1 more unit of cancer, but it was really costly for the Teflon company to get rid of Gen X from its production process. Okay? There we're going to have a different preference over the two policies to think about. Now, I mean, I'm going to give you the pure theory, the Weitzman theory from the 1970s. If you're a practical person, and I tell you that you know, there's some risk that, well, we don't really necessarily know what the shapes of all of these curves look like. But if I were to ask you, just from a very practical perspective, should we have a carbon tax or should we have a carbon standard? If the downside of being wrong about these curves is that the social marginal cost curve is really steep versus the private marginal benefit curve being very steep. So on the private marginal benefit curve side, as we're about to see in a second, that would mean that there's going to be big costs on firms for cleaning up carbon. They're going to come in and complain a lot about that. The flip side would be social marginal cost curve is really steep. Boston's underwater, like under 10 feet of water. We probably would, we might lean towards one policy over the other, aside from sort of the economic arguments and the graphs. If we just have some uncertainty about which model is right, there's probably a tendency with things where we worry about ice sheets falling off to stay away from taxes. That's the gist of it, okay? But we should kind of look and see what's the problem with standards, okay, just so that we're being fair to both sides of the argument here. The problem with standards is that they're very rigid, okay? So if you put a standard in place, the firm can't make any more pollution, and it might be really, really valuable to the firm to make additional pollution because they don't have any way to get it out of their production process. So here, what that means in graphs is that the marginal benefit from emissions curves gets really steep. So as you start to get less and less and less emissions, the value of an additional unit goes way up. And you could even have a marginal benefit from emissions curve that asymptotes, right? So beyond some certain point, you can't reduce the emissions anymore. You have to have some of it in your production process, right? And with carbon, that's anytime you burn something, you're going to have carbon unless we perfect carbon capture. You're always going to produce some carbon, okay? So here, if we're wrong, we have the standard in place. We would have liked to have been at this point here between the two triangles. If the standard were in place, we're going to be stuck down here, and we're going to get this big red triangle where the private marginal benefits from emissions are exceeding the social marginal costs. Right? So these units of emissions are really valuable, and we would have liked to have had them produced. Whereas if the tax had been in place, we would have produced too much, but because the social marginal costs of every additional unit aren't very big, that translates into a pretty small little blue triangle. Okay? So the downside here is that the firm is paying a lot to clean up. The downside back here is that Boston's underwater. Okay, that's on the graph. I didn't draw the two triangles to reflect, they both look about the same size, but in reality, that's the kind of thing that we might be kind of thinking in the back of our minds. That the blue triangle back a few slides could be a lot bigger than the red triangle if I were to draw them proportionate to the damages that we were talking about. Okay. Right, so you're going to get a question on the problem set that asks you to sort of diagnose which policy is better. If not in the problem set, there'll be one on the exam, maybe both. So where I give you various functions to describe these curves, and then there's some uncertainty about them, and you need to sort of back out what these triangles look like in some form or another and tell me which one is better policy. So pause and make sure everybody's got this. This is sort of a key theoretical idea before we complicate it a little bit. All right, so another Harvard professor came up with this complication, the Weitzman's graph, and he did this in the 90s, so this is a much later idea. But there's one story we can tell where scientific uncertainty starts to matter. And scientific uncertainty, which means uncertainty about how damaging the pollution is, can matter if it happens in conjunction with strategic uncertainty. Okay? So before I go through the graph, let me give you an example of why that might actually be true. We'll just jump up 2 slides here. Like, why would we think this kind of correlation is real? Or am I just making this up because it looks nice on a graph? Well, here's a real simple example of when the marginal benefit from emissions might be big at the same time when the social marginal cost from emissions is big. And this is pretty easy to argue because it basically just flows out of temperature and hot days. Okay? So when it's hot out, the pollution that you make is going to be more damaging. In particular, if you go back to the first or second class, we talked about how nitrogen oxides, NOx, combine with VOCs and sunlight on hot days to make ozone. and then people with asthma can't go outside, right? So temperature makes this bigger. And on days when temperature is really high, what does everybody want to do when they're stuck inside because of the ozone problem? They want to crank up the air conditioner. So the power company can sell a lot more power, and if they're in California and they're bidding into a generation system, they can actually get paid more for it. So the benefits from making another unit of NOx are bigger when it's hot because everybody wants to buy your electricity, and the social marginal costs of the NOx are bigger at the same time because of the atmospheric chemistry. Okay? So if that's the case, we can go back to the picture. And now that we wake up and it's hot out, and the marginal benefit to the firm of making NOx is bigger, and the social marginal cost of every unit of NOx is higher, what is that going to do to our choice of policy? Well, if we put the standard in place, we'd be stuck here at E hat. If we put the tax in place, the firm is only going to care about its private marginal benefit, which is higher, and the tax that they pay, so they would go all the way out to this point. Now the problem with the tax is it's just on the day when the firm wants to make more pollution that the pollution is really bad, right? So those two things together mean we'd actually like to not be somewhere in the middle here, right? I've drawn these two curves to basically have the same slope. That was the symmetric butterfly from a few minutes ago. But now because of the fact that the pollution is worse on the day when the firm wants to make more of it, we'd actually like them to be back further to the left. That there's the dotted circle, right? So if I find the two deadweight loss triangles associated with that, I switched it by accident here. I wasn't paying attention. The red one is now the tax, right? Where the firm's going to be all the way out here. The social marginal cost is bigger than the private marginal benefit for every unit back to there, right? The blue triangle is now the one from the standard, and you can see it's a lot smaller because on the day when we don't want the firm to be making much pollution, the standard doesn't let them do it. Right, so it collapses that down. So even without having tipping points or without having funny shaped social marginal cost curves and private marginal benefit curves, we still end up with one policy being better than another. Okay, and in particular here, the standard is going to win out. So in a bunch of these settings, you find the standard tends to be better. And the standard tends to be better in cases where we want the firm to do something, we don't want to give them any flexibility. Right? So that's the case with tipping points. It's the case with the correlated uncertainty here. When the uncertainty goes, the correlation is positive. So when one curve is high, the other curve is high. Both of those are situations where we'd like the firm to kind of be constrained. Okay? So you will see people making arguments in the newspaper that a cap and trade system is better than a tax on carbon because it restricts firms' activity, and they kind of talk about this in a vague sense. It's good to just rein firms in, not give them all that choice. And there is actually an argument for that. Right? We've come up with a couple of stories here that make that case. Okay. So you may see some complications like this on a test or on a problem set. And we'll give you some questions to kind of get used to that. Yeah, 2 questions. Go ahead.
Is it possible to have negative correlated uncertainty?
Yeah. Yeah, I mean, you need a story, right? And the easy story that I can come up with is the one where they're both high at the same time and then the tax is bad. But if they're negatively correlated, then on a day when the pollution is particularly valuable, it would be particularly unharmful. And then that would be a day when we want to let the firm make all sorts of pollution. And that would mean that you'd want to give them the tax, right? So that they could really stretch it out. Yeah.
I think it's a really similar question,
Yeah.
but like then could you have like a marginal benefit that's low in correlated and like one that's like high? Like could you just have them be like kind of arbitrary and both high or both low? Or
Yeah, I mean that would be potentially negatively correlated,
Yeah.
right? I have a harder time coming up with a story where the pollution would be really valuable on a day when it's also not very costly. That's kind of the dream scenario. It works really well. But you do see lots of, I think, examples like this. Because usually when we want something really bad, it's because it's nasty out. We want to be able to use a lot of electricity or power to avoid the nastiness, and the nastiness makes the electricity that we're generating more harmful. It's true of a lot of different kinds of generation capacity, besides mostly fossil fuel things. Okay. All right, so we'll play around with those kinds of graphs problem sets next week. Let's go through the last kind of model. Now this one's going to require you to think a little bit differently because the trade-offs and things that we're putting into the model here are going to be different. They're not, the graph will look a little bit the same. We're going to have a marginal cost of abatement curve, but after that it's all different. Okay. So the idea here is that I'm going to be really extreme in terms of how I talk about climate change, where essentially the social marginal cost of another unit of carbon today, let's just say the actual cost today is 0. Right? So that's a harder argument to make when there's 3 hurricanes currently churning in the Atlantic, because it's easy to argue that those are being driven by warmer ocean temperatures. But let's just say we haven't seen an example yet today of climate change in action. But in 100 years from now, we could see extreme examples of climate change in action, or with some possibility, we'll wake up in 100 years and we'll all have been a mistake and there'll be no climate change at all. Okay? So if you are a believer in climate change and you want to be able to confront people who make arguments that we don't know any, we need to wait on the scientific evidence, if that's sort of the argument that you're confronted with, this is your model. This is the one you want to draw on the napkin and try to explain. This makes the case. Okay? Right. So in general, CO2 is something that doesn't have a cost today. It has a cost in the future. CFCs are also a warming gas, and they have a cost today, but it usually comes in the context of ozone depletion. CFCs are bad ozone depleters. But the cost in the future for both of these could be big because they stay around for a long time. When you put a ton of carbon into the atmosphere, it stays there for like 100 or 200 years. It doesn't break down fast. Okay. So there's a lot of things that we could do to avoid that future calamity with some probability. With some probability we're going to have future calamity. There's a lot of things we could do. We could reduce our consumption of fossil fuels. Right, a gas tax would do that. We could subsidize renewables. The extreme sort of arguments get into like not letting people have so many kids because people generate carbon, not just by driving stuff, but by breathing. You could try to get carbon capture in your coal production or any other, the natural gas production. We heard a radio story about that. So there's a whole suite of things you could do. Some are expensive and some are cheap. All right. The argument that we're going to work through here basically relies on the fact that there's cheap things that you could do today, and then you could also implement them again in 100 years from now. Okay, so both today and in 100 years, we're going to re-implement a policy. We could do something today, or we could do nothing today. In the future, we could do something, or we could do nothing. But we're going to have the options available to us in both periods, and we're always going to want to do the cheap thing first. Okay, so the argument, it's actually pretty intuitive, but it was written down by a group of, these are actually I think OR guys, operations research types, back in 1992, so really early in the climate change debate. And back early in the climate change debate, there was a lot of discussion of we don't really know what's going to happen. Climate change might not be real. But these guys wanted to argue that even if it isn't certain, we still want to do something today. We always want to do a little bit of effort early on, okay? So to make that case, we just need a little bit of math. All right, so it's a simple model, at least in the slides. We can complicate it in problem sets and exams, with just 2 periods. So the 2 periods, I'll call it current and future. Pick your favorite climate model, and maybe that's 100 years from now, maybe it's 50 years from now. But we're just basically gonna cut the world up into today and tomorrow. There's gonna be 2 possible states of nature, so to simplify the world down in that sense too. There's the good state, which means that nothing actually happened. And we're gonna simplify what we need to do in case we're in the bad state, which is total catastrophe, to say that you have to do a sum total of 1 unit of carbon abatement. So 1 unit is the total amount of carbon we needed to take out of the atmosphere to prevent the end of humanity. Okay, we'll go to the full end of the spectrum in terms of catastrophic outcome. So now the question is, if there's a probability of being in that bad outcome, and for now we're just going to call it P, and we can move the probability around. Okay, so the probability of being in the good outcome when there's only two outcomes is just 1 minus P. What's going to be our optimal level of abatement to do today before we realize the uncertainty? Okay. All right. Now to make this argument work, this is where the chemistry, the atmospheric chemistry for carbon starts to matter. We're going to realize the fact that greenhouse gases, CO2 in particular, is what we call a stock pollutant. Okay? So you put a ton of carbon in the atmosphere and it sits there. And from the point of view of our model, it just never goes away. All right? It's just there forever. And it's going to have a cost associated with it, you know, either the catastrophic cost with some probability, or with no, you know, zero probability, it's not going to be a catastrophic cost. But what the stock pollutant means for us is that if we do some abatement today, we're taking something out that won't be there in the future. And if we don't do the abatement today, it's going to be there and it'll be there again tomorrow and add to this total stock of concentration. Okay? So we're going to have two periods of abatement activity. The abatement today we'll label as A1, the abatement tomorrow, future abatement we'll label as A2, and the sum total of the amount of abatement we do, so this is the amount of carbon we're taking out of the atmosphere, is going to be A1 plus A2. Okay? This is a model about abatement, not about emissions. Just keep the direction on the graph that we're going clear. Okay. So this is pretty much the entire argument right here. Just to make sure you understand this slide well. If we do a unit of abatement today, we take 1 more ton of carbon out of the atmosphere today, then in the future, what are we going to have to do? Well, with probability P in the bad outcome, I said we're going to have to take out a total amount of carbon equal to 1 to keep the world from collapsing, okay? Which means that in period 2, we're only going to have to do 1 minus A1 if we did A1 today. That's the amount that's left in the total abatement we have to do to keep the world from ending, okay? With probability 1 minus P, we wake up tomorrow and we realize that the A1 we did was a waste of time, and A2 then would just be 0. Right? We're not going to do any more if we realize that we didn't have to do anything in the first place. Yeah?
So when you say probability P, that's the probability of having a bad outcome?
Yeah.
So if you want to have a bad outcome, then in A2 would be 1 minus A1?
No, so the bad outcome is exogenous. We're going to wake up and nature is going to decide whether climate change is real with probability P or not real with probability 1 minus P. That's going to happen regardless. Today we're going to decide to have done A1 units of abatement, which could be positive or it could be 0 if we pull out of all the agreements. And then if we find out that the world actually, that nature was going to give us climate change, so the probability reveals itself and climate change is real, now we're stuck doing, if we didn't do anything today, we're stuck doing 1 whole unit of abatement tomorrow. Okay? If we had done a lot today, then tomorrow we don't have to do as much. But we run the risk of waking up tomorrow realizing we didn't actually have to do very much, or we didn't have to do anything and everything we did was a waste. And now we have to kind of live with the regret that we wasted money doing climate change abatement today. Okay? So all of this is going to kind of work itself out through the fact that we have an increasing marginal cost of abatement curve. I'll wait till we get to the actual graph to talk about it on a graph. But there's going to be some things we can do abatement-wise that are cheap, okay? Like, for instance, just increasing the CAFE standards on big trucks and SUVs. We reduce a lot of gas burning just by, you know, making those subsidies essentially that we're giving to American automakers because they make most of the SUVs and we want to keep them in business. That's responsible for a lot of our carbon emissions. So we get rid of those and it would actually be just a big gain. But then there's expensive things we can do today, which would be, for instance, switching the power grid over. Right? We have a bunch of coal-fired power plants that are still pretty useful. And if we have to get rid of all of those and turn them into gas plants or, you know, into solar fields, that's going to cost us a lot of money. So what that looks like in practice, this is from an actual consulting company's carbon. This is a marginal cost of abatement curve in reality, okay, so from a real consulting report. So we draw these marginal cost of abatement curves, and they're nice straight lines that slope up. Well, what they look like in reality is this consulting firm argues there's some things you can do that actually have a negative cost of abatement. So by doing this particular activity, you'll save the firm money. Consulting firms love to tell you that you can fix up your procedures and your processes and actually save money in the end, right? Because that sounds really good coming from your consultant. So switching over your heat or your light bulbs and these sorts of things, they say will save you money in the long run. Then you get into the things that have positive costs associated with them, like, you know, putting solar panels on rooftops. That's not cheap, but it's going to save a lot of carbon. And then you get to the things that they argue are really expensive out here on the end, and this is switching your coal power plant over to carbon capture, switching all your coal to gas, okay? Switching all the cars, the entire fleet of vehicles to hybrids. They don't even put electric cars on here, but that would probably be the next step. Okay, so these marginal cost curves do exist, and you can kind of see that they look like what we draw in class. Here's what I drew in class, right, where the marginal cost of abatement now goes in this direction. So I still draw it like a marginal benefit from emissions curve, but that's marginal, increasing marginal cost of abatement, just like on the last page, it was going in that direction. Okay. So over here is switching your power plant from coal to gas, and down here is putting LEDs into all the light bulb sockets. Okay. All right. Now here's the intuition for the Mann-Rochel's model, and then we'll do the calculus on the next page, and then we're pretty close to done. It's not a long model. All right. The idea here is that if I do a chunk of abatement today in the current period, and I've identified that chunk of abatement, which is blue line segment, so I take out a piece of emissions and I clean it up. And I take out purposefully the stuff that I can clean up the cheapest. So I'm down on the low end of the marginal cost of abatement curve. I'm doing all the light bulbs, and I'm taking away the subsidy for SUVs, okay? Then with some probability in the future, I'm going to have to do a total of 1 unit of abatement. But with some probability, I'm going to have to do that. And if I do, I won't have to do this part over again. Yeah?
How did you switch them? Like, how did you move it from that one end of the curve to the other?
Yeah, so the idea here is essentially if I take 100 tons of carbon out of the atmosphere today, I don't have to take 100 tons out tomorrow in the case where I actually have to do the cleanup.
Yeah.
And under that circumstance, I'm not going to do the cleanup associated with the really expensive stuff.
Oh, I see.
Okay? In words, I'm going to do light bulb switching today so I don't have to do switching of my coal plant to carbon capture in the future. I can do light bulbs today, and I can do light bulbs again tomorrow, right? It's probably not that simple because I'm not going to save the world just by switching over to LEDs. But I can avoid doing the really expensive stuff if I do some work today. That's the intuition of the entire model, right? And if you're arguing with somebody about climate policy and you want to make the case really simply without getting a napkin out and drawing graphs, you can just say, look, we can do some cheap stuff today that will save us from having to do the expensive stuff tomorrow, and you've basically said everything here. Okay? Yeah?
How come the blue A1, that was the cheap stuff,
Yeah.
now turns into the most expensive stuff tomorrow? Like, if you're comparing, say, like A1 and
Yes.
just changing light bulbs and whatever, then, like, how does that become the more expensive part of what you have to do?
So the thing is that the gas is fungible or exchangeable on the x-axis. So if I save a unit of, if this is 100 tons of carbon and I take it out of the atmosphere today, because it's a stock pollutant, then it's not there tomorrow. And I could say, well, the stuff I took out today, if I have to clean up this entire amount, right? So I made it so that 0 to 1 here is the amount I have to take all of that out of the atmosphere in the future if climate change is real. Well, I mean, the part that I'm going to not take out in the future is going to be, I'm not going to do the most expensive stuff that I avoided doing by doing the light bulbs today. And the stuff I'm left with having to do is the cheap stuff again, right? So I can reinstall light bulbs LED light bulbs in 100 years from now and avoid making the carbon from those emissions for very little cost and not have to do the expensive stuff. Not quite. This is the part that always throws people, so I'm expecting a lot of people might kind of not, probably not alone. Let me try one other way to explain it, and then maybe that'll stimulate some questions. The other way to look at it, economists love marginal things. Okay, we're always talking about making trade-offs at the margin. The other way to look at it isn't to look at taking like this section of the 0 to 1 out and taking that savings and applying it over here. That's kind of the first argument that I made. The other way to look at it is, when I get to this point right here, the marginal cost to me of doing one more unit of cleanup, the very next unit that I would clean up has a cost of the height of that line. It's whatever the next thing was on that consulting graph that I showed you. The idea of marginal analysis is that what I want to do is clean up today until the cost of the very next thing that I'm going to do is equal to the cost of the thing that I'm going to avoid in the future, right, with some probability. So the thing I'm going to avoid by doing one more unit of cleanup today is whatever this thing was right here. If I go one more unit there, then I can pull back one more unit over here, okay? Whatever that thing is more expensive than this thing was, but with some probability I won't have to do this, right? So what I'm going to do is I'm going to weight the probability of having to do whatever this thing is. Maybe this is solar on all the rooftops, okay? I'm going to weight that by the probability that I think climate change is real. So maybe that's like 60% times the solar powered thing. And then I'm going to decide, is the cost of doing that just equal now to the light bulbs that I install? Yeah.
What I'm not understanding, I think, is that, okay, fine, I get what you mean by like bringing the cheapest like abatement first, and then saying that because you are avoiding some pollution, so therefore you can avoid the pollution. I can understand that. But what I'm not getting, I think, is that how are you avoiding, like, the area of those shapes, right, is kind of representative of the cost and the abatement together, right?
Yeah, this trapezoid there, maybe this is number 5, this is the cost of the avoided cost of not having to do those units of abatement.
Right, I just don't get how that, because I thought, like, in theory, shouldn't the area of that small triangle in the current graph equal the area of the trapezoid in the future?
So the thing is that you can do cheap abatement today, right? So let's just say that maybe this is the thing that throws people off, because this is essentially what I'm saying. Is you do light bulbs today, and that's going to take enough carbon out of the atmosphere that I don't have to switch my coal plant over. Which sounds kind of crazy because there's not that many light bulbs, right? We're not saving that. We're going to do enough cheap things today that the length of that blue line is the length of this blue line, and we're going to avoid the expensive things tomorrow. The height of that thing is just the fact that we're lucky. If I don't have to do these 100 tons of carbon abatement in the future, I can avoid things that cost a lot but still take out the same amount of carbon as the things that were cheap.
But then how are you filling the entire, because you've done the entire from 0 to 1.
Yeah, so I need to do the rest of this, the yellow line I still need to do in the future period.
Right, but like what's like that cheap thing you didn't do in the beginning that's now cheap to do in the future? That's what I'm not understanding. Like,
so you can, the Man Rochelle's model says that you can do the cheap thing both in the current period and again in the future period. So I can put all the light bulbs in as LEDs today, and then in 100 years I'm going to have to replace them all either with incandescents or LEDs again. And if I replace them with LEDs again, I'm going to take carbon out of the atmosphere. I'm not going to be putting that carbon in the future either, so I'll get back this far again. And I've already saved this carbon from the LEDs I put in today.
Right.
So in the end, I basically get the whole triangle out of LEDs, which is really inexpensive because I did part of it over here today when I can pack it into the right-hand side of the triangle. You always want to stay as far over to on this graph, the right-hand side of the triangle as you can get, because that's the cheap stuff. Okay? So by doing a little today, we avoid doing the expensive thing tomorrow. We're staying at the low end of the marginal cost of abatement curve. okay, to put it into words. Yeah.
Does this model hold like all expenditures equal and like interest rate with inflation?
So, I mean,
and
the
stuff?
one thing you could add, and this is, we're gonna talk about discounting. This is where normally in the next class I would talk about discounting, because it kind of is coming out in this graph, although I haven't mentioned it. But we're gonna do the tradable permits and then talk about discounting. But we would probably argue that the cost in the future should be discounted back a bit, because we could take money today and put it in the bank and it would be worth more tomorrow. So money today is worth more than money in the future. You get into complications, and I'll save the complications for the discounting class, but the answer, that discussion is not that simple when you talk about things over multiple generations. There's a lot of argument about what the discount rate should be. So you're correct in that that should be showing up when we go from current to future, but I'm going to save it for now. Yeah. Okay. So are we closer, or?
Like, I understand when you explained it in like the marginal cost way.
Yeah.
I guess it just,
Okay.
still a little, like, it's not very intuitive.
That's fair.
Yeah.
Okay, I'm going to keep going. Here's the marginal cost way. Actually, I should have probably switched graphs. I'll keep going, and this is something I expect people want to come talk about. Basically, the idea here is, yeah, the last unit of emissions that I saved over here cost me this blue line, and I want that to just be equal to the yellow line over here, the next unit that I now don't have to do in the future, because if those two things, in expectation with probability, because if those two things weren't equal, say it was more expensive in the future, that would mean that I didn't do enough here today. The savings in the future would be bigger than the additional cost today, right? Deflating that by the probability I'm ever going to incur it. And that would mean I should be doing a little more today. So I could solve out for the optimal amount of abatement by basically trying to set those two things equal in expectation. In math terms, and we'll finish up with just these 2 pages of math here. In math terms, this boils down to minimizing the expected total cost of all the abatement over all time. So if you don't like the intuitive story with the graphs and the pictures, the math story might make more sense to you. 1/2 A1 squared is the cost of abatement that you're going to incur today if you do A1 units. So just to give you the picture, if I do A1 units of abatement today, the triangle here has an area of 1/2 base times height. And I've drawn the graph so that I just made the slope equal to 1. Keep life simple. So that triangle there has an area of 1/2 A1 squared. And then with some probability, I'm going to have to do the remaining 1 minus A1 squared in the future. So that would be the triangle over here, right? The 1 minus A1 part times base times height 1/2. So this triangle here. So I'm minimizing the sum of those two triangles packed into the right. Yeah.
How did you put A1 as the price and the abatement?
I didn't put it on the graph, but the slope is 1.
No, but like how did you slope is 1, but like the cost of the abatement there is equal to the amount of abatement?
Yeah. So basically, this curve here is just this line that's equal to A1, right? So for every unit that I do, the cost goes up by 1 unit.
Sorry.
The graph, I should have even written that on the annotations, or got it on the main graph so it'd be clear. But I'm just assuming an easy slope. On a problem set question, I might say that the function is not just 1. So then that'll just translate through into the math, okay? But you're trying to get the area of those two triangles. With probability P, you're going to incur that one. With probability 1 minus P, in the future, the abatement you would do would be 0. Okay? So those are the 3 pieces. Today with certainty, tomorrow if there is no climate change, tomorrow if there is. Okay? 3 pieces. So you take the derivative of that thing with respect to A1, I can write it as just a function of one variable, set it equal to 0. You can check the second order conditions if you want to, but they'll hold in this setup that we have here. Solve out for what A1 would be, and you end up with this function here. Okay, so just a little bit of algebra. The key thing is that P gets bigger, you're going to do more today. But even if P has to be 0 before you'd argue you do nothing. Okay, so you're always going to do something as long as there's an infinitesimal little chance that climate change is real. And on the other side of it, if you're 100% sure that climate change is real, how much abatement would you do today?
The whole triangle, right?
No? If P is equal to 1, then A1 is 1/2.
1/2.
Right?
Yeah.
So this should hopefully kind of drive the intuition home. You always want to stay on the right-hand side of these triangles. So if you know climate change is certain, so the probability part is gone, I would do 1/2 today, and that means I only have to do 1/2 tomorrow, so I would do the cheap 1/2 again. But if I do any more than 1/2 today, I'm doing stuff that's more expensive than what I would have to do if I just saved it for the next period. Okay, it's always about changing the light bulbs and avoiding carbon capture. That's the key. All right, so I think there's people outside waiting to come in, so I'm going to stop.